Alright, it really isn't as hard as it looks. Let's start with some assumptions. Assume that Church Street is slightly inclined at an angle theta, let's say about 8 degrees. But for now, let's work with the dummy variable theta. And let's assume that the car produces a skid mark S, which is about 15 meters long. Now, the coefficient of friction, let's assume that is mu equal to 0.6. And we also have the mass of the car. Let's denote it by m. And then there is gravity equal to 9.8 meters per second square. And finally, let's assume that the car is moving uphill. Let's assume that the initial velocity of the car is equal to v before it starts braking and comes to a halt at the end of the distance s. And this v is really the number we wish to find to determine if the driver was above the speed limit. Of course, the car comes to a halt at the end of the distance s as it moves uphill. Okay, with all these assumptions in place, let's get cracking. We have to somehow think of a framework that brings together all these different parts of the problem. The first thing to recognize is that there is energy in the system, initially in the form of the kinetic energy of the car, which is equal to half mv square. Then what happened? The car came to a halt, so the kinetic energy is gone. Where did this energy go? Well, it's been transformed into different forms of energy. While the car was braking and creating those skid marks, it was also dragging itself uphill. So by the time it comes to a halt, it has acquired a little height up the incline. This is the height h. And from basic trigonometry, this is equal to s times sine theta. And therefore, a part of the energy when the car has come to a halt is equal to mgh, which is equal to mg times s sine theta. But there is more. The road is not perfectly smooth and will have some friction. So some of the original kinetic energy of the car has been lost in overcoming the opposing force of friction. Now remember, from the law of conservation of energy, energy is neither lost nor gained. It merely changes form. In this case, kinetic energy, half mv square, has changed into the potential energy, which is mgs sine theta, plus the energy needed to overcome the force of friction. Now the energy required to overcome friction is equal to the friction force, let's denote it by F, multiplied by the distance, which is equal to S. Therefore, the energy related to friction is F times S. So what is this frictional force F? We know that the friction created between two surfaces, let's assume that the surface, one of the surfaces is flat, is equal to the normal force, which is equal to the weight of the car, which is equal to mg. If the car is moving in the rightward direction with velocity v, the force of friction will act leftwards and is equal to mu times mg. But in the case of an inclined road, we have to make some adjustments. The weight of the car, mg, points vertically downwards. Since the car is moving uphill, the friction force will point downhill. And now also note that the force mg, which is acting vertically downwards, makes an angle theta with the line that is perpendicular to the incline. And this angle is theta because the road itself is at an incline of theta. And so the angle between two lines that are perpendicular to the original two lines must also be theta. Therefore, the force that is perpendicular to the road is mg cos theta. Therefore, the normal force is also mg cos theta. And therefore, the friction force F is equal to mu times the normal force, which is equal to mu times mg cos theta. So, work done against friction, or you could say the energy dissipated in friction, all that burning of the road, all that smoke, is equal to mu times mg cos theta times the distance, which is s. So now we have all the pieces of the puzzle from the law of conservation of energy. Half mv square is equal to mg s sine theta plus mu mg s cos theta. This can be written as mv square is equal to 2mgs multiplied by in brackets sine theta plus mu times cos theta. Notice that m cancels across both sides of this equation. Isn't that amazing? The mass of the car really doesn't matter in determining what that initial velocity of the car was. Now, when theta is small, and in this case it is small, just 8 degrees, we can do some approximations. For example, sine theta is approximately equal to theta. But we have to be careful. This theta is in radians. Now, 180 degrees is equal to pi radians, and pi is approximately equal to 3.14. Therefore, 8 degrees is equal to 3.14 divided by 180 multiplied by 8 in radians. Also, remember that when theta is small, cosine of theta is approximately equal to 1. And so, v square simplifies to 2gs multiplied by in brackets theta in radians plus mu. And therefore, the velocity v is equal to the square root of 2gs times in brackets theta plus mu. Plugging in these values, we get v is equal to square root of 2 times 9.8 multiplied by 15 times in brackets theta, which we had calculated earlier, as 8 times 3.14 upon 180 plus mu, which is equal to 0.6. And therefore, v is equal to 14.74. And this is in meters per second because we have been using SI units consistently all through. Now, speed limits are usually in kilometers per hour. So we need to convert this into kilometers per hour. Now, 14.74 meters is equal to 14.74 divided by 1000 kilometers. And 1 hour has 60 minutes. And 1 minute has 60 seconds, so 1 hour has 60 times 60 seconds. Therefore, if the car has traveled 14.74 meters in a second, it will have traveled 14.74 divided by 1000 multiplied by 3600. This would be the distance in kilometers traveled in 1 hour. And now we'll use a calculator. And we get V is equal to 53.1 kilometers per hour. And in Bangalore, that is unheard of speed even when the roads are empty. The driver was clearly overspeeding and deserves a costly certificate of appreciation from Bangalore Police, otherwise known in Bangalore as a challan. Here's to the amazing citizens who know their calculations and do their bit to help Bangalore Police keep the traffic moving.